Hello, it's Keith here, and this is the first in the 68000 YQuest series. Well, what's YQuest? Well, you can see a few of the versions here. YQuest is a little game I've written. It's based on the Simple series, and it's a recreation of an old game I used to own on the DOS systems. This is a game called, it used to be called YQuest, so my name's a sort of parody of that, but it was really to show that the Simple series example we used in the past can be extended to make a reasonably playable little game, and you can see it here. This is the Neo Geo version. The graphics are done with a fixed layer, so the movement's a little bit jerky there. So if we just close that one down, but we can see it on a variety of other systems. This Sinclair QL here, for example. This is a version that's using basically bitmap graphics, so you can see the movement's a little bit smoother. So that's YQuest, and we'll be extending it later on to use hardware sprites as well. So at the moment, it is either using bitmap graphics on the systems that have got a software bitmap screen, or it's using the tilemap on tilemap-based systems. So in some systems, the graphics are a little bit jerky, but we'll be improving it later on. And really, the point it's supposed to make is that, from the Simple series examples, you can extend it and make a little game that's reasonably playable. And also, the source code for YQuest is free; it's open source, and you can do whatever you want with it. So you can download it and improve it and make something better from it, hopefully. So anyway, that's what YQuest is, and that's what it's intended to do. Now, what I'm going to do today is I'm going to give a brief introduction to the common code. That's the multi-platform code. Now, this was originally compiled for the Z80 and then ported to the 6502 and 68000. I'm going to give a brief introduction to it because I think it's important that I give you a description quickly of how the underlying code works, because that will make it clear what the platform-specific code's doing. But what we're going to do today is we're going to discuss the memory layout and the data structures and just a brief other bits of the game. I'm not going to discuss the multi-platform code. What I'd suggest you do is, if you're interested in that, and I'm not saying you shouldn't be, but please take a look at the Z80 version. There were 5 tutorials on the multi-platform code. The code for the 68000 version is virtually identical because it was, in many cases, I've got a converter I wrote to convert code, so the variables are the same, the label names are the same. It's just that the code is the 68000 equivalent, and I don't want to spend 5 lessons discussing the exact same thing that hasn't really changed in any meaningful way. So today we're going to give a brief introduction to the 68000 version, the memory layout and things. We're then going to go into the platform specifics and discuss what's had to actually happen for each system with regards to the bitmap graphics and the joystick and things like that, because I think that's probably going to be a better use of everyone's time. Okay, so let's go into the code and let's have a look at it today. Now, YQuest uses a bank of memory for the settings, the position of each of the objects, the enemies, and the position of the player, the number of bullets that have been shot where they are, the current level, that kind of thing. And so we've got this data structure, which is defined as the YQuest RAM. We're going to discuss this data structure today because that's sort of important to understand how the actual code works with regards to how it controls objects and things. Now, most of the objects in the game, essentially except fonts, really use an 8-byte structure to define their existence in the world. The first one is the sprite number, which is effectively actually a tile number in most cases, so that's the graphic that is being used to represent that character. Now, the YQuest sprites use a total of 4 banks of 16 sprites, so there's 4 frames of animation for each sprite, so that's not actually represented here. This would be a number from 1 to 16. The animation is constant for all sprites. It just sequences between all 4 frames and then rotates back through. Now, the next byte is currently unused in this example, but it's actually going to be used as a hardware sprite number later on. So that will be a hardware sprite at a later date. We've then got the current XY position of the sprite, the acceleration, what direction it's currently moving in and how fast, and we've got a program. Now, this is a logical routine that defines how the object moves on its own. Now, some objects, like the player, don't move on their own, so that would be program 0, but other ones will define, is this a fast-moving object? Does it randomly change position quite often? Does it seek onto the player? That kind of thing. So that's used by the movement code to decide how to move the object. Collision programs define how the object interacts with the world. Now, if it's a 1, then that's a crystal. So if the player touches it, they will gain a crystal. If you get enough crystals, you win the level. That's good. Anything else will hurt the player. Bullets will not hurt the player. Obviously, they'll hurt enemies. And then you've got 255 is an undefined object. That's an object not drawn to the screen. And 254 is a dead object that's going to come back later. So this program is effectively the movement routine, and collision program is effectively the sort of logic routine, if you will. And there's 8 of these, and they're defined for basically every object in the game. And you see, that's the object layout. Next, we've got the X and Y position. That's for font drawing. We've got the sprite frame. As I said, there's 4 banks of animation, and that's just defining which one is which. You can see all of these definitions are relative to the previous one, so we can just relocate the entire bank just by moving the original YQuest RAM or user RAM. That's the intent here. The bullet array is the player bullets. There are a total of 8 on screen maximum, so that's defined there. You can see it's 8 bytes because it's the same format as this here, and there's 8, so it's 8 times 8 here is the offset. We've got the object array, which is basically again the same format, but that's got a total of 40 objects. That's the crystals, the enemies, the mines, things like that. So that's everything except the bullets and the player. We've got the invincibility counter. This is a byte, and that's just basically the player can't be hurt at the start of the levels. A random seed, that's 2 bytes. That's for the random number generation. A key timeout. Now, when you're accelerating, if you hold down a button, you'll get faster and faster, but you don't want to get faster too quickly. So during the timeout, the key presses are ignored. The lives is the current number of lives the player has. The level is the current level the player's on. The crystals is the remaining crystals on the level that the player needs to collect. Some levels might have a lot of crystals, like a level could have 40 crystals, but we only show 40 objects on screen. And so what we do is we only show 5 of the crystals, and when the player collects 1, it will respawn until all the crystals have been collected. Playing SFX is the current sound effect. We use Chibi Sound, which is the little driver that I discussed in the platform-specific series. We're using it again here for simple sound effects. Playing SFX2 is the previous sound effect. That's to see when we need to change the sound. So if it was making a beep and now it's silent, for example. Score is the current score in binary coded decimal, the same as the one we used in Yquest68000. It's the same code. High score is the best score so far. Again, same format. Player object is exactly the same format as this, but this is the player, so this is the Y of the player, and you can see we've got pointers to the individual elements just for convenience. So if we want to change the player's acceleration, we can just use these labels here to directly address the acceleration of the player object here. And last pos X and last pos Y, this is used during the movement code in the same way as the simple series. If an object has hit the wall, we need to reset its position. So these are just some temporary variables to do that. So there we go. So as I say, the really important take home from all of this is that every object in the game uses this same object layout with 8 bytes, and that when you have a bank of 8 objects, each of those 8 objects will have 8 bytes in this format. So we use offsets to these within an object to control the object. Okay, so that's the RAM definitions. Now the next thing is the data definitions. These are the fixed values that the game uses to define things. Let's take a look. So first of all, we've got the starting definition of the player object here, which resets the player at the start of a level. So sets the player position to the center of the screen, 0 is the acceleration, and so on. We've then got a few definitions here for the constants of the game, the byte size of the object, which is of course 8, that's that thing again. We've got the number of enemies, we've got the bullet count, and we've got the on-screen crystals here. So this is defining the constants for the game here. Now we've got the level map. Now there are 16 levels defined in the game, and once you've won them all, they just loop around. It goes on forever. So we've got a set of long pointers here to the actual level definitions here. You can see them. And so these are pointing to these, which are the actual definitions of the levels. Now each level is defined in a fixed format here. The first byte is the number of crystals you have to collect on the level. The second byte is unused. It's just to maintain an even format here. And then we've got definitions of all of the objects. Now to end the list, effectively ending the level definition, we have a 0, which is an empty object, and then 255. You see, it will keep reading in this sequence until it's completed the 40 objects of the level. So by having 2550 objects, you basically guarantee that the level definition will finish here. So this is defining 3 of object 1 here, which is known as the slow purple. This is defining 3 of object 2, which is the crystals. Now notice there's a difference between the crystals you need to collect and the crystals that are shown on the screen at a given time. And then we've got mines here, so we've got 5 mines with object 4 here, and then we've got 255 of object 0. And you can see these progress, and as the levels progress, there's more and more enemies and potentially even more crystals. We go up to 5 crystals maximum, and as you can see, it gets crazier and crazier, and then the last level has tons and tons of mines and seeking purples. Quite annoying there. And these are just some templates for objects if we want to add a new object to the level. So you can reconfigure the objects by tweaking those. Now, each of these pointers to an object type, for example here, 11 is a joined 0, are defining a lookup in here. Now this isn't, unfortunately, I possibly should have changed this, but this isn't in the same layout as the object layout here. It's using this slightly different version. So we've got a sprite number, collision program, an X acceleration and a Y acceleration. So these are being held in here, and you can see that the format here, so the first one is the sprite, the next one's the collision program, then there's the program, then there's the X and Y acceleration here, and these are the object types. And so as I say, each of these is an object type relative to this, so you can see that that's defined by this object type here, and that's got the sprite number, the movement, and the programming things. Okay. We've got some random number generators here. These are going to be used by the random number generation code. It's actually based on the random number generator I wrote for my Chibi Aliens game. And then what we've got here is just some strings here to be shown on the screen. Now I don't think these small ones are actually used by the 68000 version. All the 68000 machines have decent sized strings, so those probably aren't needed. But as I say, these are the messages that are shown to the screen in my classic 255 terminator string, which is what I use in my tutorials. We've got some binary coded decimal scores here. Basically, they need to be in the same format as the variables in memory. My addition routine adds 2 variables of the same length, so that's how we add scores. So we can add 1 point, 3 points, 5 points here. And this massive bitmap here is the title screen, and you can just about see a Y here, I think. And then there's that weird rabbit thing there. This is the title screen in the same format as the sprites. So this is sprite 0, which is effectively blank when the title screen drawing routine runs. That's sprite 10 and so on. So this is drawing the title screen using the tile or sprite graphics of our game. So just a simple little graphic there. We could have made this a bit more efficient because it's only 0 to 15. We could have actually used 1 nibble per tile, but its size wasn't particularly a concern for me, to be honest. So we didn't do that. So there we go. So that's the common code there for the data definitions and the RAM definitions. Now, if you want to see the multi-platform code, as I say, this is it. All of this, of course, is available for download on my website. But as I say, I'm not going to go over this because, as you can see, there's rather a lot of it. So it would take really 4 lessons or something for me to do that. And as I've said, the code is basically identical with regards to the label names and the function of each section to the Z80 code. So please take a look at the Z80 code so that I don't have to make 5 lessons that would be basically repeating myself. Okay, so there we go. Anyway, we're going to be continuing with the YQuest series. We're going to go over each platform's version and discuss any particular details of those systems. You know, as I say, it's basically a extension of the simple series. It's just now been turned into a game, and we'll be discussing each of those later on, and where appropriate we'll be adding hardware sprites as well. So hopefully you'll stick around to see that. So there we go. So that's the YQuest series. Yeah, as I say, you're welcome to go to my website and you can download the source code for these. And what I always say with these episodes is you're welcome to use the source code in any way you want. If you somehow manage to make a commercial game with this as an example basis, then good luck to you. You don't need to give me credit for it or anything. I don't care. It's really, as I say, it's an example that's hopefully going to help you get started, make your own games, and just make the point that, you know, from a relatively simple beginning of the simple series, we can actually end up with a decent game as a result of it. So there we go. I hope you found this interesting. I hope you'll give it a go. I wish you all the best with your programming projects. Thanks for watching today, and goodbye.